We make a jump to the next part. And the final R thing will be a short one today, since we already did a lot there throughout the other ones. But anyway, correlation and regression. Now, I started out with correlation. Then I talked about regression. Correlation was a symmetric kind of way of looking at it, of the XY situation. Regression is an asymmetric one, where we decide on which is going to be the Y and which is going to be the X in order to put a line in. And it makes a difference, actually, which is X and which is Y. However, there is also a relation between the two things. We're not going to heavily dwell on these technical relations, but just say that the correlation coefficient and the slope coefficient, we could say, or the slope estimate, are connected to each other by this sort of some of the same amounts, like this. So we could express them from each other using just a sort of formulation of things, using the building stones of SXX, SXY, and SYY. This is a repetition. The correlation R expresses, as I've said previously, the strength of a linear relation. The B quantifies explicitly what it is, right? How does Y relate to X? 1 unit of X gives this change of Y on the units that we use of X and Y. R comes with no physical units. Beta comes with units, right? The Y units as a function of X units. And here's another technical thing that we can use for interpretation. Funny enough, if we take the correlation coefficient, which is a number between 0 and 1, then if we square it, we could sort of see it, if we want, as a number between 1 and 100%. If we should say we could multiply by 100 if you want, and then see it as percentage. If we square the correlation coefficient and see it as a percentage, it's between 0% and 100%, right? 0 correlation means 0%, 1 correlation means 100%. And then we have something in between, from 0 to 100%. And this percentage has an interpretation. It has an interpretation as a percentage, and that is what we see here. Not so much this one, but these two actually. Let's not focus on the math. We cannot, in a way, understand anything from this mathematical expression. It's just a fact that it can be expressed like that. What you can understand is, try to follow me in, that the Y variability can be seen as consisting of two things. So the differences in our weights as a person, as here from person to person, the differences in weights is two things. It is a difference that comes from the fact that we have different heights. That's one explanation, right? So we have a difference if we just take from person to person, we have different weights, yeah. Part of that can be explained by the fact that I'm not so tall and you're taller. So the fact that you have a higher weight than me is to some extent at least explained by the fact that you're taller than me, right? But that doesn't explain everything. We can take people of the same height and still realize that we are not the same weight, all of us, as I've said a few times. So, variability in weight is explained by height, and then there is a remaining unexplained variability. And this percentage, in fact, is exactly the squared correlation. Of course, you need to go through sort of the formulas to convince yourself that this makes good sense, but I'm not going to do that to you now. I'm just going to tell you that does make sense. I would like to add a bit on the plot here just to illustrate this. I included now these plots in the one I'm going to share with you. Here is the plot for the 24th sample from all of you. The thing is, the average weight was how much? Let me check that. What was the average weight of the sample? 73 kilos. We had some, this is of course also the difference. We probably maybe had some female sampling also now, not only males. So we got a more joint weight average and not just a male weight average here. Here is Y bar. That was 73 kilos approximately. If we put in this one here, then if we were going to find SYY, which would be the first step in finding the variance of Y, not thinking about X whatsoever. But let me illustrate on this picture what if we were going to compute the variances. That would be each individual Y subtracted using its own average. That would be like these bars here. Now like this. All of these would be yi. These are yi minus y bars, right? This is a rather big number. There's a large y variability going on here. Now I could instead do what is expressed in SE squared. That would be starting out by taking, let me not write out the formula again actually due to the time. That was taking each individual yi and comparing with the line, not with the y average. And these, the sums of those ones are much smaller, right? So we have some variability. Residually after we have looked at the line, and we have some raw variability. The line explains something and there's something left. That's basically the point I wanted to make. Here we are. Let me finish this correlation and regression part by just very briefly mentioning this. This is not something I'm going to enforce on you. You could do statistics on correlation also. We compute correlation, we compute intercept and slope. I've spent some time on telling you how to do statistics on intercept, slope, and the line. In certain situations, you could do statistics on the slope computations also. At least if you have data where both x and y are random, like my height and weight, it could make sense. And there are pages telling you how to do confidence intervals and how to do hypothesis tests on the slope. The good news is that the major test for relationship between x and y, that would be a hypothesis of no relation that would say the correlation is 0, which is the same as saying that the slope is 0. Those two tests are the same. So we don't have to worry about a lot of new theory for the correlation because we can make this hypothesis test by the theory that I already gave you for testing the slope. It gives us the same result. So that's the good news. We don't have to spend a lot of energy, and that's why I sort of cut it out a little bit. It's there, it could be done, but I'm not going to enforce it on you. Right, that's the short thing. Let's make the last jump to the last part, 5 minutes.